All right, our next speaker is Kang Kim from the University of Pittsburgh, and his title is Ultrasound-based Hybrid Imaging for Comprehensive Diagnosis.
How does this point to? Is there any laser point? It's the Okay, thank you. I was quite overwhelmed by the title of this workshop, The Next Generation. As I barely worry about my research in the next 5-10 years, at the most this generation. But I will try to introduce what we have been doing and then what our vision of our lab as well under this title. So as we know that diagnosis in clinics is made through physical exam, radiology, imaging, and pathology test. That the motivation here is that advances on imaging technology may partly cover or complement and miss some other exams. For example, the physical exam, such as palpation, can be covered that assessing the tissue stiffness using elastic imaging. So there are efforts in society that using MR elastography, ultrasound elastography, the conventional compressional elastography. Also, there are also shear wave elastography as well. And there is an effort in vibroacoustics as well. And also, some of the part and anatomical pathology can be covered by using a compositional imaging technology, looking at the composition of tissue, which is important signature of the progress of disease as well. And there have been efforts using OCT, they call a virtual histology, and ultrasound MR as well. And then some of the metabolic changes, such as like molecular pathology, can be also assessed using molecular imaging, traditionally PET using radiolabeled tracers, MR, CT, ultrasound using a corresponding contrast agents targeting to the specific biomarkers. There can be an argue, for instance, for example, molecular imaging versus pathology, that people can say that blood tests, for example, the assay, in vitro assay versus molecular imaging can have an advantage in that they can be highly multiplexed, and then they can assay thousands of biomarkers simultaneously. But the molecular imaging, the blood-based test in vitro assay can only provide an average information. Then molecular imaging can complement providing a temporal and local information, which is sometimes very important to detect the progress of disease locally and also to assess the response of the treatment. So I just quote here from the book, the excellent book Molecular Imaging recently came out, written by Weisselder and other papers, Gambier and Stanford, that he said that a combination of these strategies, blood protein biomarker test and molecular anatomy imaging will play an increased role in clinical disease management in the future by complementing each other. And the molecular imaging will continue to fundamentally change the understanding of biology, pathology, and clinical management of patients as they assess all these biomarkers under physiologic condition and under biologic condition versus an in vitro assay, which I use as a textbook in my multimodal imaging classes in bioengineering department at Pittsburgh. So today, the motivation and outline of my talk is that as I'm going to introduce the ultrasound-based multimodal functional imaging to assess the mechanical, the stiffness of tissue, and compositional, and the biological changes by using the elastic imaging to address the mechanical property, and thermal strain imaging, again using ultrasound, the composition or composition of the tissue, and combining with laser photoacoustic molecular imaging to assess the bioactivity of the human body. And then I'm going to introduce as a focus on cardiovascular application we emphasize in our lab. So here the little image that as you have a bloodstream with cholesterol, cellular waste, and the lipid contents that may deposit in the underlining of the blood vessel that may thickening and stiffening and reducing the blood flow. But this is okay when you stays like this, maybe reducing blood flow, but when it ruptures, that's the end of story. It leads to a major cardiac events such as stroke and heart attacks. So the question is that to the clinicians in clinics, the physicians, that it's very hard to know what kind of plaque and when and how they rupture is critical information they would like to gather to address a accurate diagnosis. So this is kind of from your left to right, how the progress of atherosclerotic plaque, that it's thickening and larger, and then composition and mechanical property changes. But some of the plaque will rupture and some do not. And people have found the ruptureness of the plaque does not depend on the size of plaque. So what they have found so far is that there are various features of the rupture-prone plaque that is lipid-rich central core with thin fibrous cap. And then ongoing active inflammation on the thin fibrous cap is continually weaken the fibrous cap. And then there is a vasovasorome grows in to feed these necrotic pores. And there is internal hemorrhage is another signature of the rupture-prone plaque. And there is also microcalcification that reside on the, especially on the surface of thin fibrous cap, to resist against the continuous pulsatile flow generating stress on the thin fibrous cap, and it rupture and break. So these are the signature of the rupture-prone plaque, and then our motivation is to assess these parameters using a single modality. So this is again another cartoon that this is a lumen blood vessel, and from the beginning as a leukocyte recruited to the endocellular cell, as it progresses, there is a compositional and structural changes until it ruptures. There is a mechanical property changes due to this development in blood vessel. And there is also a compositional changes, especially the large lipid cores. And there is an ongoing inflammation from the beginning stage of atherosclerotic plaque to until it ruptures. There is an ongoing inflammation. So I would like to introduce the ultrasound hybrid imaging to address these parameters using ultrasound-based system. So out of these three, 2 out of 3 that I would introduce first, ultrasound elastic imaging and thermal or temporal strain imaging to address the mechanical and compositional in conjunction with a B-scan, which is free for ultrasound. And then I will introduce photoacoustic molecular imaging at the later. So the underlying physics for combining ultrasound elastic imaging and thermal strain imaging is there are 2 different physics, and we use one technique, and you get 2 images plus anatomy co-registers imaging. So tissue elastic property, the stiffer, the smaller mechanical strain will generate. Then we address using ultrasound elastic imaging. And tissue composition, especially lipids, and there is a sound speed decreases in lipid, and while as the sound speed increase in water-bearing tissue as temperature increases. So we use this sound speed changes. As sound speed changes, there is a variation of propagation distance appear either closer and farther away, may generate some strain. It has nothing to do with mechanical strain, but it does appear it might have generate some strain that we call either temporal strain or summer strain. And then to address these two, we collect RF data and using one technique based on spectral trackings. And as we address these two different strains, which look similar on cardiovascular system, and there is a challenge to separate these two, and just relevant way is you just ECG gate to eliminate the mechanical strain out of your thermal strain as temperature increases. So this is a nice figure that Ben Burr summarized all these ex vivo measurement of the different tissues that the measurement has in x-axis this is temperature changes, and y-axis is the sound speed in the tissue. And what we noticed is that most of the water-bearing tissues, as temperature increases and the sound speed increases, whereas the lipid-bearing tissues, as temperature increases, that sound speed decreases. It's a very subtle change, but one goes positive, one goes negative, which is a great contrast to image. So this is very simplified. I do not want to go over the mathematics here, but the sound speed is a function of the temperature changes, and that temperature is proportional to the absorption and the input energy and heat capacity and density. As the temperature increase in the tissue, that generates sound speed changes that appear closer and further away, and it has a linear relationship to the temperature rise, and we ignore the thermal expansion in the range of the energy that we use here as we increase only temperature 1 or 2 degrees Celsius, and we just increase very slowly. So this is this is real data. That the top one is a data collected using a single element transducer shooting ultrasound from gelatin, and bottom is in rubber. As we increase the temperature of that tissue phantom and gelatin, you can see actually time goes by. Not the signal actually comes one towards to you, one goes the other way, the other direction. As sound speed increases, that it comes toward to you and it looks further. So one, you can generate a negative strain, on the other one, while the other one generate a positive strain, a contrast of plus and minus. This cartoon illustrates more explicitly that, say for example, you have ultrasound transducer, and you have object A and B in non-fatty tissue, and you have object C and D in fatty tissue, and as you increase with whatever method we use, ultrasound here, increase the temperature, when you echo those things, you will have A, B, C, D, and spacing like this. But as time goes by, increase temperature, the sound speed increase in water-bearing tissue and decrease the fatty tissue. The object of A, B, C, D looks closer as it propagates further, and B looks even further closer. And while as the C in fatty tissue, as sound speed goes down, C looks further, and then as it propagates, it looks even further. Looks like these AB get closer, generating a compression, and these CD looks like separate, looks like expanding, but this is not a mechanical strain. It's just a temporal strain generated due to the change of sound speed by temperature. And then if you have those strains, then we encode those strains, negative as blue and positive as red, then you can separate these two tissues in imaging. So just to prove a concept, we borrow a HIFU transducer, which is designed for high-intensity focused ultrasound surgery. And we just drive very gently. We don't want to ablate the tissue. We just drive very gently enough to increase only 1 degree Celsius of your phantom. And the pulse sequence, like your heating and pulse echo imaging and heating, and you collect the data. And this is a canine kidney, not just any specific reason for disease, but we know anatomically in canine kidney there is a fat substance there. So we did apply our thermal strain imaging on that, and then collecting the data, as you can see here, as time goes by, the contrast comes up with red indicating lipid here, and then the other kidney is full of water here in tissue. As in gold standard, we did histology that tells you there is a fat here at the center. And we also compare TSI, a well-known MR fat quantification, that this is MR imaging, and MR has a great capacity of quantize the fat, which matches very well with our identification. That we were very happy in a sense that this is almost real time. What you see here, that as the time goes by, to reach to this point, the signal processing took only 3 seconds. And also to demonstrate the feasibility that can we do this one on commercial ultrasound transducer that we had in Sony's Touch, and we coded our heating pulse and imaging pulse into there, and there is a phantom with the inclusion of rubber that just for the proof of concept, as we increase the temperature, we were able to detect this lipid surrounded by gelatin phantom. Just to demonstrate that can we apply this technology into commercial scanner. And then, if we can do, then we might be able to combine ultrasound elastic imaging and thermal strain imaging as we do a similar data acquisition on the same setup. So this is a rubber phantom, pulsatile by pulsatized by pulsatile pump, and then we had the ultrasound, and we applied our thermal strain imaging sequence while we collect RF data, and synchronize to eliminate any mechanical strain generated by this pulsatile motion from the thermal strain imaging. Then we were able to separate those signals that on the left here in color code, red means expansion as it goes like this, and then blue means it's compressed. So it expands on the side and compresses in the middle. And then inclusion was harder than the surrounding. That tells from elastic imaging that it is harder. And then when we gate it, only separate this to separate this mechanical strain out of thermal strain, that we were able to detect, oh, there is a composition of lipid, which was rubber, compared to gelatin tissue here. When the pump was on to gate to the pulsatile pump, just to validate, we just pump off and then do TSI, which we should get if the gating was perfect, but we were happy with this much of artifact. Might have due to with the imperfect synchronization, and also might have due to with this motion that might have been in a differential field, while as this pump off stayed in one acoustic field when we hit up. We show we demonstrate the feasibility of this concept using commercial ultrasound, but this obviously has a limitation. Just because this transducer was designed for imaging, not for delivering energy to heat tissue. So this is the imaging transducer we were able to show, but it has a limitation as we measure the beam pattern of that transducer in our water tank. When we mapped out that, even though we applied some beamforming, put in some beamforming efforts there is an parts. So for example, if you needed this much of energy to heat up 1 or 2 degrees Celsius, there is a risk on behind at the focus that it might overfocus and dose more energy. So when we think about translation into clinics, this may cause some problem or address some safety issue on this one. So instead of keep playing using commercial ultrasound transducer that designed for imaging, we decide to build a optimized transducer to deliver efficient energy to heat up the tissue temperature within 1 or 2 degrees Celsius, larger area with no worry about overfocus, with the collaboration of Doug Stepan, UC Davis. So, and then we came to the optimal design in terms of frequency and imaging depth and beam size that integrate into commercial ultrasound transducer. So this is prototype that you have a heating transducer over here and integrate into a commercial, this is Vivo 2100 system that you hit with this transducer and imaging this one, just to show the feasibility. When this works, then we may have to put some efforts to package this into a little larger probe than imaging transducer there. So to show the feasibility, we did phantom study, but we also did have a the human blood vessel that we hook up to the same system that we showed did on phantom study and connected to pulsatile pump, and we had using now this transducer heating and this transducer collecting the data. As we have this one that we had a very encouraging result on this blood vessel samples, and we found from mechanical strain elastic imaging tells that fatty parts, which is evidenced by the histology here, is softer and hard, meaning that there are lipid and soft that increase the specificity of these lipid components in blood vessel. So with this encouraging in vitro result, that we conducted the animal study, a rabbit model, which is well known in society, that we administered high-fat, high cholesterol for 5 weeks before we do a injury. Ultrasound guided, you induce the balloon and then rubbing against the blood vessel to cause some injury. In conjunction with this injury, and high-fat, high-cholesterol diet will develop a plaque here. And then after that, we apply the TSI, UEI, on the animal using that system I showed in the previous slides. That we had, so using either sonic touch to show that it's like the clinical, close to clinical use in using the clinical scanner, and to increase the spatial resolution, we use also high frequency imaging system as well. So, for example, this is control rabbits. So then when we apply, this is the femoral artery. When we apply the TSI, that it shows most of places is blue, meaning that it's mostly like water-bearing tissues. And with some red, which is known that in adventitia there is some fat in normal tissue. And then the histology tells us it's very clean and water-bearing tissue. And this is a rabbit with high cholesterol, fat, high cholesterol diets with injury that from 8 weeks, actually this is control, and this is 8 weeks after, and this is 12 weeks after, that as you can see here, the red tells the spread of the fatty composition, and comparing with this whole blood vessel, oil red or staining. So these are, to do this, those animals should be different. But we also did a monitor on one animal from 4 weeks and 6 weeks and 8 weeks and 10 weeks, and resect, and it says that there is a lot of fat. As you can notice by color, blue lipid water bearing, and red is lipid. As time goes by, you can see in this region that you can see as red developed a fatty deposit and more spread out and then high fatty concentration toward. And then now if we, as I said, that we can do hybrid imaging UEI and TSI all together, that the plaque at the bifurcation evidenced by Doppler, that you see that there is a feature over there and then reduced blood flow over here. That on that, if you apply ultrasound elastic imaging and Summers strain imaging, tells that there is a hot, fatty, and then blue means it's softer than the surrounding tissue. So the intermediate summary on this talk is that the preliminary in vivo and also ex vivo human tissue result that demonstrate of the feasibility of this UEI, TSI to assess both the mechanical components, characteristic, and the composition of the tissue. And as we have this one, we can have as UEI, TSY compared you have either one single modality. As you have more parameters here, you can increase the specificity on identifying the specific tissue here. And there is some still issue that even though we spread out our beam and we know that it doesn't increase more than 1 or 2 degrees Celsius, but when you think about translation, they always ask the feedback. So we are working on this for further translation of this technology. And with that, it's not only morphological, the compositional and mechanical change. We need some metabolic changes to detect, to address the vulnerability of the plaque. And the motivation, with that motivation, we propose and combine with photoacoustic molecular imaging. Just for those who are not familiar with photoacoustic imaging, this photoacoustic phenomena was originally invented by Barry Graham, who invented a telephone, and he heard the sound when his invented telephone diaphragm was exposed to the light. Then he heard whispering that he named a photoacoustics. Was completely buried until 1970. People start developing a stable laser lights to test in a systematic fashions, utilized for crystal components and chemical component in air and condensed materials. And maybe 10, 20 years back, people start thinking about, can we use on biomedical applications using this contrast? And that's the photoacoustic imaging effort in biomedical applications led by the leaders in the society, Li Hong Wang, Orievsky, and we have Dr. Curie-Yakub here as well. So the photoacoustic is when the laser lights is observed by any contrast in the tissue, it will generate by this Summers extension. So light is observed, and then by energy conservation, this short pulse laser will be released mechanically and expand, and it generates very short pulse, which is very wide band signal. So this is, we did some FE-based simulation that top part is the laser source, and the laser goes by and it will exposed to the target will be observed, and then it starts generating. So this is light source, and this is red, and blue is the wave or front that it generates sounds. As I can run this boom, and then so the energy source to detect is a light, and we forget about light, and then we listen to the ultrasound. So the motivation here is that you have a full range of different imaging modality and penetration depths and resolutions on each. And then the motivation is you can have a photoacoustic imaging with a reasonable imaging depths of up to 4 to 5 centimeters with very resolution with very high frequency ultrasound ranges. Photoacoustic can be done, as you can imagine, on natural optical contrast, but our motivation is to detect the inflammatory biomarkers. So we use in the vehicle of contrast agent molecular probe, a gold nanorod. The reason that we chose is that gold nanorod, depending on the aspect ratio, the absorption peak can vary. Meaning that if you can select a specific wavelength to specific particles, you can detect multiple particles at the same time, meaning that you can interrogate multiple biomarkers at the same location as you synthesize nanoparticles bind to the specific biomarkers on each aspect ratio. So the idea is that you have gold nanorod as if we are interested in specific biomarker, for example, ICAM1, which is one of the inflammation biomarker, we bind to the anti-ICAM1 and let it bind and shine 700 nanometer, which is absorption peak, and then it will beep. So I will skip all these process, how to bind antibody here. So we use as a test bed a animal model that we shine the laser to induce the injury on the endocellular cell. After you inject rose Bengal dye with the chemical reaction, you injure that cause inflammation. And then we have made of these nanoparticles, nanorod at different aspect ratio and conjugated with different biomarkers. And we inject this one. After you inject that one, then you image using now photoacoustic laser source tuned to those nanoparticles wavelengths, and you listen to the beeps. Then wherever that it has a beeping sound is the site where the antibody found the antigen or corresponding antigen. So it's a schematic idea that this is a lumen, and you injure using photosomal injury, and there will be at the injury there will be an overexpression of ICAM1 and E-selectin, and more, and then we inject the cocktail of these different nanoparticles of ICAM1 bound and E-selectin bound, and inject that the antigen will find the antibody and line up. Then if you shine a 750 nanometer, only these particles will beep. If you shine the 800 nanometer, only these particles shine. Then we know that at this site there are ICAM1 overexpression, and there are also E-selectin overexpression, this much and that much. So this is our preliminary result, that this is the IVC, and this is the site where the injury happened. And then this is the photoacoustic imaging, and before injection, of course there is some signal there as a natural background absorption of the tissue, also generate some sound. And then after we inject, that the injured site just brights up as nanoparticles gather together and generate photoacoustic signal. And this is a composition of these morphological information with this metabolic information together. And then we also did the cocktail of the two particles at different wavelengths targeted on different biomarkers. And this is before injection. And this is after injection. As you can see, the increase of between this and that, and this and that, telling that there are ICAM1 and E-selectin overexpression in this blood vessel where it was injured. So with that, I would conclude introducing the vision of our lab is that we would like to integrate all these technology into, hopefully, in one scanner in clinics so that it can address the morphological and mechanical, compositional, and metabolic information on this scanner. And then application varies a lot. And we just named this one as Octosonics, as like octopus in the future, that scanner. All these lines are our resource funding sources. Some are pending until this can be taken over by company, will be a line of source of medical expense and insurance. So I have other projects going on in the labs, but without the help and collaboration inside University of Pittsburgh and outside, and my postdoc and students in here, that this would not happen. So I would appreciate all those people and conclude. Any questions?
Time for a few questions.
Do you find position stability to be an issue or something that might make these calculations work?
I'm sorry?
Position stability, is that an issue for a lot of these calculations, specifically like for the thermal imaging, if there's a position drift in what you're imaging?
Oh, okay. There's any physical motion on this?
Yeah, if there's organs moving within.
Right. It's a great question. That's another challenge that we try to overcome. If there is any like cardiac, actually it's easy because if you do ECG gate, you can eliminate. If there is any translation, it sucks. But because this is you calculate strain, the translation can be eliminated if you take the derivative. Yeah. So that's.
On the position part of the thermal imaging, what you call thermal strain imaging, can you give me a sense of resolution?
Sense of what?
Resolution.
Oh, resolution.
And what kind of
right. You mean spatial resolution. The spatial resolution directly depends on the strain calculation, which is, yeah, so within the range of, say, like for 5 to 10 megahertz transducer, we can have theoretically 150 to 250 microns, but with some filtering, all those things, it can go up to 500 microns. If you use higher frequency, you can get higher.
If you look at the lipid in a typical plaque, what is the size?
Oh, it could be depending on the size of your blood vessel. So if you go to coronary, it can be challenging. But carotid is our kind of now the target just to demonstrate the transcutaneous approach. And it could be a few millimeters in size, without beauty.
And how do you distinguish normal motion, normal tissue motion? Most of the stuff that you showed was in vitro type. Normal tissue motion, how do you
mean normal, like we just discussed, the cardiac motion can be gated. So if you gate ECG, then you can eliminate the mechanical strain out of this TSI, thermal strain.
Have you done that?
Yeah, that's the result that the animal study we have done is actually ECG gate. And we also developed some other modality, signal processing, we call time series analysis, to also, just in case the ECG fails and noise, that as a complement we have other signal processing technology.
Right. Thanks
Can
again.
you tell when you're looking at fatty plaque which ones are likely to rupture and which ones will not?
When I looked at the fatty stuff.
Can you suggest which ones will be likely to rupture?
Oh yeah, so I mean, I'm not a physician, but from the medical society, in the medicine society, the large lipid core is one of the big signatures that you may rupture. So in combination with the large lipid core, surrounded by, for example, thin fibrous cap developed with calcification, is highly going to be ruptured. So in other efforts that in our lab is we actually try to develop a prediction model on this one by modeling the tissue.
And you have enough resolution to see the carotid artery with the skin?
Yeah.
All right. Last question.
How do you see the regulatory issues?
I'm sorry?
The regulatory issues, the FDA requirements.
We haven't gone to that far. The challenge is we kind of think ahead that there is a safety, So do you have a feedback mechanism which we are working on those things in terms of signal processing and in terms of electronics? And there may be some shutting off things that we are working on those things.
So the regulatory issues are the heating of the tissue is the primary.
Right. So we plan to change our technology. When we say thermal strain, heating, then people worry about are you heating the tissue? Well, actually we're warming 1 or 2 degrees Celsius. So we may change our word called temporal strain instead of thermal strain.
All right. Thanks again.